Hi, I'm Mr. Miller, and this is a lesson on the factor theorem. So we're going to start with a numerical example. If I divide 30 by 2, I can do this the long division way. So first I'm going to try to figure out how many times does 2 go into 3? Well, of course, that's just one time. 1 times 2 is 2, and there is 1 left over. If I bring down the 0, then I know that 5 times 2 will give me 10. And there is nothing left over, so a 0 remainder. Now, when we did the remainder theorem, we would write the quotient here as the quotient, so 15 in this case. And when we had a remainder, we would go plus the remainder over the divisor. The thing is, in this case, the remainder is 0, so actually this term is not necessary to write. So now if we take this division and rewrite it as a multiplication to understand the relationship between these three numbers, we've got 2 times 15 is equal to 30. All right, so keep those things in mind as we go on now and take a look at the factor theorem with polynomials, and it should help your understanding. All right, and now we are looking at notes on the factor theorem as it relates to polynomials. So the factor theorem states that in a polynomial p of x, x minus a is a factor if and only if p at a is equal to 0. So yes, you heard me right. I said if and only if. This is a bidirectional statement, and it means that if x minus a is a factor, then p at a is going to be equal to 0. And likewise, if p at a is equal to 0, then x minus a will be a factor. So in this first example, we would like to show that x plus 1 is a factor of this cubic polynomial using the synthetic division and also the factor theorem. So what I'm going to do is I'm going to start with the synthetic division. So dividing by x plus 1, we put a negative 1 inside the box here. We put the coefficients of the cubic, starting with 2x cubed minus 5x squared minus 4x plus 3. We leave a little bit of room down here at the bottom for the quotient, and then the remainder will go here. So let's take a look at doing this synthetic division. We copy down the 2, multiply by negative 1, we add with negative 5, multiply by negative 1, add the negative 4, multiply by negative 1, and then add the positive 3 to that. And we end up with a remainder of 0. Since we have a remainder of 0, that means that x plus 1 is a factor. Now we can also substitute negative 1 into the polynomial and evaluate. And here we find that the value we get is also 0. So again, this is a remainder of 0. And when we have a remainder of 0, this means that x plus 1 is a factor of that cubic polynomial. So now let's take a look at the integral 0 theorem. This states that if x equals a is an integral 0 of a polynomial p of x that has integral coefficients, then a is a factor of the constant term of the polynomial p of x. So this is really helpful when we're trying to factor something like this cubic polynomial, because we can just look at this last term, the constant term, look at the factors, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20, and one of those, hopefully one of the smaller ones, will make the polynomial equal to 0 when we substitute x equal to that integer. And that means x minus that integer will be a factor. So we don't have to completely randomly guess as to what how this thing will factor. We're just looking for, we can try out numbers that are factors of that constant term. So this is what we're going to do. We're examining the factors of 20, both the positive and negative versions of it, to see which one makes the polynomial equal to 0. Now, you can try, for instance, x equals 1, and you'll find that 3 times 1 cubed plus 5 times 1 squared minus 12 times 1 minus 20. Well, that would be 3 plus 5 is 8. Take away 12 is -4. Take away 20, that's -24. It's not equal to 0, so x minus 1 is not a factor. And if you also tried -1, you would find that it's not a factor. But if you try evaluating this polynomial at x equals 2, this will give you 0. So that means that x minus 2 is a factor of this polynomial. So we can rewrite this polynomial in factored form once we do the synthetic division, or long division if you're really into doing things the long way. So I know that this 2 value makes it equal to 0. X minus 2 is a factor. Again, we use plus 2 here. And the coefficients of the cubic, 3x cubed plus 5x squared minus 12x minus 20. Now I leave room for the quotient and the remainder. We copy down the 3. We multiply by 2. We add 5, multiply by 2, add -12, multiply by 2, add -20, and we get a remainder of 0. Good, this is what we were hoping for. Verifies what we saw here. Remainder of 0, x minus 2 is a factor. Remainder of 0, good. X minus 2 is one of the factors of this cubic. Here's the other factor. It's 3x squared plus 11x plus 10. So let's rewrite the cubic as x minus 2 times 3x squared plus 11x plus 10. It says to factor this cubic fully. So the x minus 2 is one factor, this quadratic is the other factor, and we should try to factor this as well. So what we're going to do is we multiply the 3 times 10, we get 30. We're looking for factors of 30 that add to 11. Well, these would be 6 and 5. Once you know those things, you can decompose that middle 11x term into 6x plus 5x, and then you can do some grouping. So if you group the first two terms here together and take out a common factor of 3x, the other factor will be x plus 2. And if we group the next two together, we notice that there's a common factor of 5 times x plus 2. And now you see that both of these parts have an x plus 2 in common, which you can take that out as a common factor. So now it's x minus 2 times x plus 2 times 3x plus 5. And now the polynomial is fully factored, and that's it. So if you're if you are in my Pre-Calculus 12 class and you'd like to see another example, you may read example 4 on page 131 and 132 of the textbook. And that completes the lesson on the factor theorem. Thanks for watching, everybody, and have a great day. Bye.